Hello, can you guys hear me? All right, I am here to introduce Nick and Electra, and they are going to talk about macOS malware in 3D using data science. And if anybody has any questions, raise your hand at the end, and I will bring a mic to you so we don't miss that. Thanks, guys.
So hello, everyone. Really glad to be here. So thanks for the kind introduction. So today we're going to talk about macOS malware in 3D using data science.
So for this portion, as you may have already seen in previous presentations, we have our forward-looking statement disclaimer. Per SEC regulations, we do like to show this, so we'll give you 30 seconds to review this. We, of course, wanted to showcase the malware 3D visualization for the start. Otherwise, we would have had this up at the beginning. But if you want to just take a couple seconds, we'll continue on.
OK, so to go back, just to show this gorgeous visualization, Nick is going to talk more about it later on. This is pivotal to our presentation. So let's start. So yeah, I'm Electra. I'm a data scientist.
I'm Nick Benyo. I am a threat researcher with Jamf Threat Labs.
OK, see you later. OK, so to start with, here is an overview of the topics that we're going to discuss. So who we are, why we are here, why our work is important, and a sneak peek into the inner workings of our approach. So what this is all about. So the current presentation highlights a successful collaboration between data science and Jamf Threat Labs that resulted in enriching Jamf's repository for the protection against malware. So what exactly do we mean by that? Let's take it from the beginning. So malicious software, aka malware, is intentionally designed to perform a variety of harmful actions for profit. Some of those malicious functions are displayed here. So a malware family is a group of applications that share similar attack techniques. Identification of the behaviors and the characteristics of a malicious software largely assists the detection and classification of malware. So how large a threat does malware impose? So we know that every day, thousands of malware and potentially unwanted applications emerge in macOS devices, and those are responsible for millions of attacks per year. So as we saw, malware distribution is prevalent in macOS devices. Their correct classification into malware families is not trivial. To add to this problem, we should also consider that vendors all use different names for the same malware families. Also, it is tricky to associate newly discovered malware with existing malware. So, for example, some questions that might arise are, did we actually discover a variant, or did we actually discover a new malware family? Furthermore, it's difficult to evaluate how well we maintain coverage for existing families through traditional metrics. So how to approach malware grouping? A way to approach that is based on the malware functionality. So the next question is, how can we detect the functional similarity of a malware to other malware? As a fact, we know that software developments mostly do not start from scratch. Their use of source code is very prevalent. It is often misused, and that's a case of malware. and it leads to a large number of clones in the underlying assembly code. We can leverage this phenomenon to build our tools for grouping malware. So how can the existence of code clones assist our quest? Let's briefly see the types of code clones. So generally speaking, there are 4 types of code clones shown here. I'm not going to go into much detail. So exact clones and clones that contain minor modifications, so the 2 first categories, can largely be detected using hashing algorithms and locality-sensitive hashing. Syntactically equivalent clones are created due to different compilers or due to different compiler optimizations and can be detected after applying normalization. The detection of semantically equivalent clones and thus the extraction of semantic similarity among malware is not trivial, and that's the case of the last type of clones, the semantically similar ones. So why is the detection of semantic similarity non-trivial? So the various compiler optimizations and obfuscation techniques can make logically similar assembly functions appear dissimilar, thus obscuring the functional relationship between malware. So to detect semantic similarity is of utmost importance to account for semantically similar code clones. So a bit more about data science now. So to quantify the similarity of a malware to other known malware, we need to extract numerical values that reflect the semantic content. So in other words, we need a process that is able to take as an input a malware file, map it to a mathematical object in such a way that encapsulates the semantics of the assembly code. In terms of machine learning, representational learning can capture and encode patterns that are found in the data and is able to map this information to a representation in multidimensional space while preserving the semantic relationships. So ASM2Vec, assembly to vectors, is a type of representational learning model. It has been previously described in a published research paper, and it utilizes word embeddings to encode the semantic similarity of the assembly code. So our approach involves several steps. First, converting the binary code of a malware file to assembly code. This first step is called disassembling, and then mapping the semantic content of the resulting assembly code using the ASM2Vec model into a mathematical object called tensor. So in addition to that, to enable the inspection of the relationships between malware files in a more human-friendly way, we can reduce the multidimensional tensor to 3D vectors. So we can extract information on similarity between malware in 2 ways. We can calculate it mathematically, or we can extract it from 3D visualizations. So the mathematical calculation of similarity between a pair of malware tensors yields a single number. So here, there are several available functions to calculate the similarity score. Here we have 2 examples of tensor representations of 2 different malware files that result into a single numerical value, and that's the similarity score. So for a repository of malware, we can get a similarity score per each possible pair of malware samples. And visually, we can leverage the 3D vectors to retrieve distances between malware samples and cluster them into groups. Nick is going to delve into that. So to wrap this up for now, the heart of the pipeline is the ASM2VEC model. So it takes as an input a malware file, which is retrieved from a repository. The first step involves preprocessing of the malware file to produce the assembly code. Then the ASM2VEC model transforms that assembly code into multidimensional tensors. The tensors are then reduced to 3D vectors, so x, y, z. And the tensors and the 3D vectors are subsequently stored into a bucket that is accessible to the threat analysts. So what are the advantages of our approach, the ASM2VEC-based one? So our approach does not rely on handcrafted, human-picked features that might introduce bias. There is no requirement of prior knowledge around the specifics of the compiler optimizations, or even the correct mapping between malware samples. Our approach is able to encapsulate the functional similarity directly from the assembly code. And last but not least, it offers two ways to extract information on malware similarity via a numerical value called similarity score, and through 3D visualizations of the malware samples. So let's see some visualization magic and threat analysis insights. The stage to Nick.
Thanks, Electra. So that was a lot of very intense data science that has been done so far to be able to calculate these scores, these similarity scores, these vectors, XYZ coordinates, which is pretty cool because it allows us to create a visualization kind of like this, right? Now, I am going to dive into why we use this 3D tool, how we use it, but I don't know everyone's background here. I don't know if everyone has background in understanding what Jamf Protect does for threat prevention, how we protect endpoints. So we're going to do, step away. There you go. Okay. We're going to do a quick refresher on threat prevention. So Apple introduced the Endpoint Security API for monitoring system events for potentially malicious activity. That was pretty critical because prior to the Endpoint Security API, a lot of times people were getting into the actual kernel and were doing kernel extensions, which could certainly lead to some stability issues. But with Protect, we use a system extension, and that sits between the kernel and the end user. The system extension is what allows us to be able to take a look at whatever processes are executing and to deem whether or not those processes are malicious or not, and to stop those processes from executing. So Protect will analyze an event. If it determines that it's benign, the process continues on. When a process executes that is deemed malicious, then Protect will kill that process. All right, so hopefully everyone's following me so far. This is pretty straightforward. When you look at the mechanisms that we use for threat prevention, there are namely 3 processes that we're using to identify and kill these potentially malicious processes that are executing. So the first is file hashes. Now that is a unique fingerprint of a file, very much like Electra was talking about. The file hash that has been deemed malicious, that has been generated through a hashing algorithm like SHA-256, is going to be on like a predetermined list. So if we see that file hash, and that's what is trying to execute, we will kill that process. The file hash can change drastically if even a single bit is altered. So similar to what Electra discussed earlier with code clones, you change one small part, the malware is functionally identical, but it's a totally different hash, right? So there are some problems with using file hashes because it doesn't take much to change that fingerprint. So it's kind of like a game of whack-a-mole if you're just collecting a list of file hashes to try and react to whatever is out there. The second is the mechanism that we use is Team ID. So that Team ID is this unique ID that developers are issued from Apple to sign whatever software they're distributing. If we have seen malicious applications associated with that Team ID in the past, in most cases, we'll block software that is signed with that Team ID. And this provides a little bit of proactive protection, as malware not yet written will be blocked if it's using that Team ID. So on some level, we know, okay, anything else that this particular Team ID is using, proactively, we're protecting you against that. And then the third is Yara. And Yara allows you to search files for specific patterns and properties. And if you can find a common pattern of malicious bytes that are associated with a group of malware, you can basically proactively protect against variants of that malware. Specifically, if you're able to tag something that is like functionally important to what that malware is doing. This ends up being quite powerful. Obviously, again, it does depend on how the Yara detection is written, but the malicious actor may have to completely rewrite their malware to avoid detection, so it definitely is going to give us more proactive protection than just kind of the whack-a-mole with file hashes. So as you can tell, based off of kind of how I've been framing this, file hashes are good. Team ID is a little bit better. And Yara is probably the best protection that we're using here for these like static threat prevention mechanisms here to block malware. All right, so we've done that like hopefully not review for literally everyone. Hopefully this is maybe someone got something out of that. But we've gone over like what the threat prevention pieces are, why we would care about file hashes, why we care about Team IDs, why we care about Yara. Let's talk about Titan and how we're using it. So that cool 3D cloud visualization that we're going to get to on the very next slide, how is that relevant? How are we using it? So new samples that we come across are largely classified by the community and vendors. And those vendors don't always agree with each other. Many of them may call it generic. Almost as important as blocking something that's suspicious is understanding what was trying to execute on your endpoint. Was it some adware, or was it like a pretty nasty Trojan by like a sophisticated group that was trying to execute? Well, it's hard to tell if everything's just classified as generic, right? So we definitely want to know what is being classified, or what is trying to execute on the endpoint. Now, related to that first example is identifying supersets of highly related samples. So, you know, the community can get, I think, overly granular. There are certain samples that we've seen which were basically kind of a potato-potato situation. We're looking at samples that have different names but are largely the same thing. This helps us identify those examples, and in some instances, we're able to actually simplify our rules and provide broader coverage by understanding the relationship between what were thought to be completely different families, but in fact are all highly related. Related to what Electra was talking about earlier, bespoke samples are of interest here because if we run a sample through the similarity model and we find it's not related to anything, that is of interest and something that we should be like researching further if we don't see anything closely related to it. So that can certainly raise interest or help us focus our efforts on things that we've maybe never seen before. It isn't related to what we might have in our current repository or database. And then lastly, this will help us analyze threat prevention and improve coverage. So again, just touching on what we were talking about earlier, if we're looking at what has Yara coverage, what doesn't, what's related, it helps us kind of extend that coverage. So those are kind of the high-level use cases for how we're using this visualization. So here we are in the Titan project. Here's the visualization. Everything was building up to this, so I appreciate everyone's patience. You did get a little teaser of it at the beginning, but we took the output of Electra's model and the XYZ coordinates that she provided us, and it was plotted in Three.js. So each tiny little dot, like each itty bitty dot in these clusters represents a distinct sample. So you can see there are a lot of samples that are creating big clusters. There are some smaller clusters. And we can freely filter between the different types of malware using kind of a drop-down selector in this tool. And that coloring can be toggled by the user to view malware by protect name, by vendor name, by team ID, by architecture, by all of these different features that we were talking about that we use when we're analyzing malware. So let's take a look at filtering and kind of how that works in action. So you can see here, this is going to cycle through several different types of samples. We've got add load, we've got bundler. I'm seeing that the colors are maybe not as vibrant as I was hoping, certainly not as vibrant as they were on my computer screen, but we're filtering through these different samples here. And this is allowing us to basically see, okay, like where do these different protect families lie in relation to each other? What if I want to just be looking at stealers? How can I drill into that and further look at their coverage? We can do the same with vendor name. So this is going to go through each of those examples, not quite as long-winded as the first one. It's going to go down to Yara hit, so we can see what has Yara coverage, look at that relation, and I think you kind of get the idea. This allows us to filter and view the different clusters according to the different attributes that they have. In this case, we're just looking at x86, and I think we switched to ARM here as well. And then lastly, there's team ID. So we could look at unsigned samples, which are also of interest to us. In this specific example, we're drilling in just a little bit. So I did mention that we're able to like change the coloring of the different samples as well. So we can change the grouping. That grouping is what determines the coloring. So you see like right here, we've got these green samples interspersed with some like pink samples. So obviously there's some vendor disagreement on what those different samples are. But we know, we kind of trust what's going on with this model, that in fact these samples are all probably related to each other, right? And so we'll actually look at that a little bit closer. We'll switch between architecture and team ID and Yara, and then finally the conclusion that we had come to with how we classified it. So you can see architecture is the same, signing ID was the same, and Yara was the same. It made sense in this case for this to all be classified as one threat, right? Okay, so you might be thinking, we're taking your word on this just a little bit on how related these are. How do we know that this is kind of working reliably, right? I think it was probably a fair question. So that particular question was answered by taking sort of an academic approach with encoders. So an encoder is something that allows us to be able to make malware polymorphic in that certain parts of the executable, they can be modified to change the hash and add randomness. Because this is kind of what we were talking about, right? We keep talking about the hash changes. You change one little bit, like how do you know they're related? Well, this is kind of a great example of that. It allows us to kind of just put some randomness in this, but is the overall structure of the malware something we can still detect relation on, right? And this is something that we were able to test using the Shikata-ga-nai encoder within Metasploit. All right, and this allows you to be able to take Metasploit payloads and encode them. Now, again, this is an academic approach that we're taking to just show that there is still relation that is able to be discerned from this model. So first, we use Metasploit to create a very basic reverse shell payload. And that reverse shell payload is not encoded. So the generated hash is this big long string ending in B2B2. Great. So we've got a sample. Let's go ahead and plug it in. So we ran this through ASM to VEC in that algorithm in order to find its closest match in our database, which came back as a hash ending in 6879A, was a 98% match. That hash doesn't mean anything to you. What does matter is that it was falling kind of where we expected it to be. We then generated the exact same executable, but this time we did encode it, Shikata-gun-9 encoder, which resulted in a hash 556935E is what it ended in. It's a big, like, long string. We performed the same check, found the closest match was also 98% in Titan. And we can see it falls within, right next to the family that we would expect those hashes to expect, or to be in, right? So we can see, oh, it's clustering with the exact same family as the original sample. So this is successfully detecting that there is similarity between these samples despite the encoding or the attempt to obfuscate the sample. And here is, in case you're wondering, the table visualization that accompanies Titan. There's the ability to see what is selected. So there's a selector in each of these videos. As that selector expands, anything that selector intersects with will appear in this table visualization. All right. So we got a couple more rapid fire examples of using this for reclassification. We cleaned up this cluster right here. I think there were close to 12 families that were clustered in there. After seeing that as a high potential opportunity to reclassify, we were able to clean that up quite a bit. You can see there's, I think, 2 or 3 in there now after we cleaned up the YAR rules. Another example with some adware that there was some vendor disagreement on. The dark blue is really not doing me any favors here. So you'll have to bear with me, but there is some dark blue right here and then some like blinding pink. And the dark blue, it looks like it shows up as like a bunch of random, like generic, rload, some general names. Like there's not general agreement on what these different samples are. So it gave us an opportunity to dive into it. These are all real close to each other. Like let's analyze this a little bit closer. And we were able to determine, actually, this is all basically just part of the adload family. And so that is something that we were able to ascertain from the Titan tool. So let's talk about a family that I was looking at recently. We'll do a dramatic reenactment, like, you know, of me like coming across this, because obviously I wasn't recording everything the moment that I was looking at it, but you'll kind of get the idea. So it's a stealer. And if you've been following the news, stealers are everywhere. We love stealers, right? Like they're all over the place. They're so hot right now. Stealers in every article that I've read this year, it's just stealers all over the place. So obviously it was like, why not? Let's start with stealers. I had to, you know. So here is our dramatic reenactment of going through, and this is typically how we're able to visually identify high potential clusters where we can say, hey, like there is an opportunity here for us to dig closer into how we can extend our coverage. We've got hash coverage for this cluster, but maybe not all the Yara coverage that we wanted. We can make our rules even better to proactively protect instead of playing this game of whack-a-mole. So you can see I'm just kind of zooming in on the, oh, wrong button. You can see I'm kind of zooming in. We'll have to start it over here. I'm kind of zooming in on this cluster right here of adload, I believe is what this is. And just jumping around, and you can see anytime you're inspecting something, you can see all of these other clusters. And let me tell you, when we first came out with this tool, it was not quite as like beautifully uniform as it is now. There's quite a bit of benefit that has come from using this particular tool. But even as I'm like cycling around, look at that right there. There is a nice little heterogeneous cluster. There's all these different colors in here. We can see it's not just all one color. We've got a lot of variability in what is within this cluster. So let's take a closer look, because these samples look like they're on top of each other, right? And so now that we know, generally speaking, it's pretty reliable to use this model, if it's saying that they're all related, they should be, right? We've switched to Yara in that example, right? Now I'm seeing there's like partial Yara coverage. Once again, brutal dark blue is just killing me here, but like the dark blue, I believe, is the uncovered. So there is a better example close up here. If you look closely, you can see there's 3 different families. The coloring in Titan is not static. So it just randomly assigns colors, which is why you'll see a difference in the colors in some of these screenshots. You may notice that purple is max stealer, orange is Vigorf, and green is generic. You notice purple, orange, and green, I'm sure, just looking at that example. We feel pretty confident that this is all the same family because of how similar they are. Now, if we're looking at the Yara detection, we have max stealer detections in red, and we have undetected by Yara in purple. Again, hash coverage for all these samples. These samples aren't going to run on your endpoint, but future samples, we want to extend that Yara coverage to be covering additional samples that may be created in the future. All right. So, kind of interesting here when we look at this red and purple unknown, because some of these samples right on top of each other, and yet one is hit by the Yara coverage, the other is not. Okay, so this is so similar. Why? What's going on here, right? Only one detected by Yara. So the key thing, I think, to take away here is that there's a lot to look at in malware, right? A lot to look at with all these different samples that we have. But this model just gave us the opportunity to find the high potential analysis that we could do, where we know if we look at this, we have very high confidence that just looking at this a little bit closer will allow us to extend our coverage. So let's take a closer look at these hashes. We've got the two hashes here, this max stealer hash, red one. We've got the unknown hash right here. So I went and looked at the actual Yara rule that was detecting on one and not the other, and found that it actually came down to a missing piece, the connection string in the binary, which for reasons that I guess only malware authors know, includes hello world in their connection string. And the hello world in the connection string was not always case specific. And so simply finding that and changing the hello world to no longer be case specific extended the coverage for these samples, and having a slightly broader connection string that we were looking for in our Yara rule extended coverage for all of these samples. So that, in summary, is what we discussed today. We looked at the state of malware, the threat that it poses, extracting vectors from malicious binaries, and generating similarity scores from those vectors, converting it into 3D vectors, and then improving protection by using a malware visualization tool known as Titan. And that's it. We do have a little bit of time for questions, if anyone has any questions.
Hello? This was really interesting. The focus of it seemed to be for research and analysis, but what I immediately thought was, like, is it possible to, when you see a novel executable on the machine, performance analysis, and then, based on its proximity to known malware, flag that as probably malware? Or is that too expensive and not something that can be done right now?
You know, that is a good question. So we have looked at specifically unexamined samples and how we would call them. Right now, the mechanism in place for that is API-based, so it's not something that's happening like locally. And there is a little bit of latency on that analysis. So I don't know about the future, just the current state. That's not like currently in the cards, if that makes sense. Good question, though. Thank you. Any other questions? Comments, criticisms, anything?
Any feedback?
Heckling. We'll take heckling at this point. Break the silence, folks. Oh, thank you. I appreciate that. All right. Well, thank you, everyone, for coming. If you have any questions that you didn't want to, say into a microphone, feel free to find either of us after the talk.
Thank you very much.